Now let's see the first problem for the article force between the plates of a capacitor. One plate of a capacitor is connected to a spring as shown in the figure. Area of both the plate is A. In the steady state, separation between the plate is 4d by 5. Spring was unstretched and the distance between the plates was d when the capacitor was uncharged. We have to find what is the force constant of the spring. Okay. Now, initially, we have an uncharged capacitor. Okay. Initially, we have neutral or uncharged capacitor. So there is no charge on the capacitor. So there would be no force on the plates. Already we have seen in the fundamental force between the plates of the capacitor. Now when it is charged through a cell V, so what will happen in the steady state? So we have seen in the fundamental lecture of the force between the plates, in the steady state, the capacitor will get fully charged, correct? And say we have a spring like this here. So positive plate would be attracting the negative plate with a force Fe, and in the steady state this plate would be in equilibrium. So there will be another force acting on it on the right side, the spring force, and this spring force will be equal to what? Correct? So in the steady state, if you make the FBD of the right plate, one force will be acting on the right side, that is the spring force. One force is acting on the left side, that is the electric force, and both will balance each other to keep the plate in equilibrium. So in the we have seen what is the electric force. So the electric force was, we have seen in the fundamental lecture, that came to be how much? Q square by 2 epsilon naught A, correct? Q square by 2 epsilon naught A. That was the electric force between the plates, and already we have seen, we have derived this Q into the separation between the plates. So if the separation is d, so we got epsilon naught A V square by 2d square. Epsilon naught A V square by 2d square. So it will be epsilon naught A V square by 2d square, and what will be d? D is the separation at equilibrium. Given at the equilibrium, the separation is 4d by 5. So now at this instant, the separation is 4d by 5. So in place of d, put 4d by 5 whole square, correct? So this will come to be epsilon naught A V square by 2 into 16 d square by 25. So you will get 25 epsilon naught A V square divided by 32 d square. Okay. So this is the electric force acting between the plates at the equilibrium. Okay. Now what we know by Hooke's law, a spring force is equal to Kx, where x is the elongation or compression in the spring. So the capacitor was uncharged. Of course, there is no force acting on the spring. The spring was in its natural length, and the distance given between the plate was d. That is the initial condition. Okay. Now the distance is 4d by 5. So what it means? It means the right plate, which has been connected to the spring, has moved by some distance. So what is the distance moved by the right plate? So it is the difference of the separation between the plates. So it will be d minus 4d by 5. That is d by 5. So d by 5 is the distance moved by the right plate, and same will be the elongation in the spring, because the spring would elongate by the same amount by which the right plate would be going side. So the spring force will be K d by 5. Okay. So we got the electrostatic between the plate, the spring force. Now at equilibrium, equate both the forces. So I'll get K d by 5 is equal to what? 25 epsilon naught A V square by 32 d square. Now simply we have to apply the basic maths. So we'll get 25 into 5 into epsilon naught A V square by 32 d square multiplied by d, that makes d cube. That is the answer for the value of K. This comes to be the spring constant. Got it? So what was the theme of the problem? At the A state, you make the FBD of the right plate. The right plate is acted upon by two forces. One is the electrostatic force, one is the spring force. And since the right plate is in equilibrium, so both the forces will be equal in magnitude and opposite in direction. Got it?